Hey, hi, I'm Jeff. Today I'm going to talk to you about a project called Skyhook, which is programmable storage for databases. This is a project at UC Santa Cruz in the Center for Research on Open Source Software. And this is work with my colleagues Noah Watkins, Michael Zavilla, and Professor Carlos Malton. And I just want to say a quick word about CROSS. So Carlos is actually the director of CROSS. And
Can you
this...
speak up a bit, please?
I'm sorry?
A little louder, please.
A little louder, okay. Move this guy up. Okay. So, where'd that go? That's a little worse. Okay, and the CROSS bridges the gap between sort of student research and open source projects. Is that loud enough? Okay. It is funded by Sage while an endowment, and also corporate memberships. There's a few corporate sponsors here listed, and the goals are to really leverage open source software culture and university research, as well as incubate work beyond graduation to reach critical mass for projects. And there's more info at cross.ucsc.edu. And Skyhook is actually an incubator project in CROSS, and it funds also graduate student research as well. Okay, so programmable storage. In this case, for Skyhook, we want to push down some data management tasks into the storage layer. You can think of things like transformations, or we're going to process data or format data. Also, maybe some metadata operations like indexing, maybe statistics, or more complicated operations. Skyhook uses Ceph Object Storage, which is open source and extensible, and originated at UCSC. And there's more information on programmability.us for the general programmable storage projects. But this talk is just about Skyhook, which is focused on data management. So briefly, if you're not familiar with Ceph, it's a distributed, scalable, fault-tolerant system. It's an object store. It's widely available in the cloud. Objects are the key entity here. Although there's other API wrappers on top. There's a file interface, also a block interface, an S3 interface as well. But the Liberados is the core library underneath that interacts with the objects. So in this work, we work directly with the Liberados library, and it allows us to interact directly with the objects. And interestingly, we'll talk a lot about the ability to create user-defined object classes. So you can think of these as sort of customized read and write methods for your object storage. And that's what the storage version, this talk will focus on those storage aspects. So data in a Ceph cluster is stored in the following way. So assume you have a few storage servers. Each has disk, memory, and CPU connected via some network. And you might take your data file and partition it somehow. These partitions can become objects. And then there's a data placement algorithm called Crush, which will decide where to place the data across the storage servers. And a few key features that are important for us in this case is Ceph has primary copy replication. Writes to an object are atomic and transactional. And given an object name, the client can calculate the location. So there's no need to look that up or ask anyone else. You can calculate that yourself directly because it's based on the placement algorithm here. Also, it allows partial reads and writes of objects. So we don't have to write a full object every time. We can read subsets of the objects. And then a nice feature is, of course, it redistributes data during failover or adding or removing nodes, just like for scalability reasons. So that's all beneficial to us because for data management, this provides some transparent capabilities to us, which is helping us with distribution and scaling. Also, of course, fault tolerance recovery. And then we're going to we take advantage of these customized object classes to get some remote processing on storage servers and queryable metadata also on storage servers via this local indexing mechanism. So on each Ceph storage server, there's an indexing mechanism, and in fact, it's a RocksDB instance. So the rest of the talk, I'll focus on these two features. So what do we mean by remote processing in this case? So we want to be able to execute custom object classes on the OSDs, or these are the storage servers. So again, we have the picture of the storage servers here. These are object storage devices, in other words. And local to every storage server, there's a RocksDB instance. And that's where we might want to put both indexes and other metadata in there. So these little red circles will indicate that the actual processing is local to the storage server. It's done with that local RocksDB. The object read and write custom methods that we're going to talk about also executed on the object directly on each server, so they can be executed in parallel on all the objects distributed on all the servers. So what's an example of something you might want to do with the remote processing capability, right? So you can think of a full-size image maybe stored in an object, and maybe you want to have a custom read or even a custom write method, which is to generate a thumbnail. So in this case, the object contains the full-size image. You might execute your customized processing method right there, have the storage server execute it for you on the object, and out comes this thumbnail. And of course, this would reduce data transferred. And if you think about it during write time, it would be the opposite. You'd store the thumbnails at different sizes that are processed right there in the storage server while you're writing. So that's one pretty straightforward example. But some other things you might want to do, you might want to do checksum. You might want to do some filtering or transformations. I might want to do some aggregations. These are some of the things we're going to do as well. Or transform or even reorganize your data with these remote processing capabilities. So notice that the remote processing, since it's happening on a storage server, it takes advantage of the local CPU and local memory to that server only. So what are some custom object classes? So this is called a CLS in Ceph. And there's a C++ interface as well as a Lua interface. And this just gives a brief example of each of these two functions compute an MD5 of the data. So in both cases, you have an input and output buffer. That's the input and output buffer to the storage system. And over here, for instance, in the C++ case, we'd read the data and then go ahead and process it with the MD5 calculation, and then append the output of that to the output buffer. So it's going directly in the read and write functions in this case. So we put this all together. Skyhook contains really three aspects. There's data partitioning, so we consider this our physical data layout and data format for our data management. The remote processing capability, as well as this queryable metadata. So what is the architecture? We have a database on top, and then there's a connector layer. Think of it as an external table interface. In this case, Postgres FTW. And it's going to utilize those Skyhook, those CLS plugins in Ceph that we built. And the architecture on the bottom remains the same. There's no changes to that. So first is the data partitioning and formatting. The important thing here is we take table data, partition it via some method. Here we partition it in row partitions. We use a hash function. It's a jump consistent hash in this case. And we end up with individual partitions of the table that contain sets of rows. And then we're going to take those partitions and we're going to format them into a data format. In this case, it's Google flat buffers, which is similar to protocol buffers, if you're familiar with that. And the formatted data is what we're going to store in the object. So the important thing is that the data format and the metadata about that format that is stored in the object really needs to, so these are one-to-one with partitions, but the partition information needs to be there. So the table semantics is retained within the format. And this really is what gives us the capability for the storage to do more interesting things, processing on the data, rather than just read and write opaque like byte streams within the data. Another thing here, we have partitions one-to-one with objects, as I mentioned, but the object names are generated, and the objects are automatically distributed by the Ceph distribution algorithm, so we don't have to worry about that. And also, the object location, because any client can compute via that function, the object location, the server that contains the object, we don't actually have to store the location of every object and keep track of all that information inside Skyhook. So these are some of the benefits that we get laying this partitioning format on top of object storage. Next is remote processing. If we want to think about what are the types of things we want to do, so again, we have a table. In this case, it's row partitioned, as we mentioned, and one partition per object. So again, a little red circle just means that's the self-contained entity that we'd like the storage system to be able to operate on directly at runtime. The operations we might want to do for a database, right, is like select like a row operations. So read subset of rows, for instance, from the object. And notice these happen independently on every object. Or you might want to do a column-based operation like project. Another thing that we might consider is aggregations. So maybe min, max, sum, count. But notice here, these are partial aggregates because they operate on those individual object independently. So it's not a global aggregate, but it's a partial aggregate. And this, of course, can still be helpful because the object function, the CLS function, can actually return just the min directly from that object rather than instead of returning all the data from the object and making the database look for the min of all the data from all the objects. So this is kind of constraining the amount of network traffic as well as the compute to actually find the min. Another operation, you can think of sort, order by grouping, things the database might need. But again, remember, these are partial. So still could be helpful, though, because you can return partially sorted data to the database and use a standard technique like external merge sort or something where you already have sorted pieces. So that it really gives both sort of the I/O reduction in these cases as well as some CPU costs that by applying these filters and all this and the projections and the aggregations on remote servers, we can save CPU time and cost at the higher level database application. Okay, remote indexing. So same thing here, we have the table data, which is one partition per object. And so say you want to create an index over a subset of the columns in that object, right? So you might want to create those locally, and that all happens object local at the storage server level, and that index is stored in a local server's RocksDB instance. So this is the subset of the data, and they're all computed independently and stored independently. So you might do single column indexes. We support multi-column indexes. We also have some text indexes capabilities. So this kind of richness allows us to do these interesting metadata management techniques. And then this metadata, in this case it's an index, is actually queryable at runtime. Right? So it's stored, because it's stored in RocksDB, you can actually query this metadata. So you can think of other things we might want to do, like compute stats. So every object can compute its own stats, store those locally, and query them at runtime. We also may want to split an object. So for some reason, if the data becomes skewed in a particular partition, for instance, or you just would like smaller objects to support maybe better scalability, this is sort of this metadata management capability in addition to indexing, but it's still going to happen on the storage servers at the object level. And lastly, you might want to do something even more interesting is maybe you want to reformat the object, right? So perhaps we stored them in rows, but now we'd like to change the orientation of the rows to columns format. So this is something that we can write these custom CLS plugin methods for Ceph to go ahead and execute for us at runtime. All right, some of the extensions we developed. So this is work in these object classes. This is under source/CLS in the Ceph directory, and there are other ones there right now. You can see them. We implement select. So from a table T, where some predicate is applied, or project, and these are the aggregations that I mentioned, as well as this queryable metadata. So notice that all of these little instances are actually those functions or those filters or that index lookup is actually going to happen at the object level on the storage server. So that's the remote processing capability that we've been developing. Okay, so some quick results here. So consider a data set. We look at TPCH line item table, which is from a database benchmark. And we're going to use 1 billion rows. It's about 140 gigabytes, roughly. And we're going to store those into 10,000 objects. So we have 10,000 partitions, and those are about 14 megabyte object sizes, each object. And then each of those will compute a local index at a storage server like we showed. We'll consider a point and a range query. Then we're going to show the performance as we have one client node, so think of it representing the database, right? And underneath, we'd like to grow the storage servers out from 1 to 16 storage nodes. So we scale out the storage and show what happens as far as I/O and CPU benefits. And then we'll compare the standard Skyhook approach, which is this query processing done remotely in that CLS plugin, versus a standard approach, which is all of the data is returned from Ceph to the client app, and the client app does all of the work up at the higher level. Right? So those are the things that are actually executing in those objects, or that number of objects, rather. So consider point query. So this is a single matching row in the entire table. So on the left-hand y-axis, we have execution time, and the x-axis shows what happens as we scale out the number of storage servers. And then we have 3 versions here. So the client-side processing, this is the standard method where we read all of the data. The storage servers return all the data to the client does all the processing to look for this row. Oops. Sorry about that. So you can see, as expected, right, you scale out the I/O as you add more storage servers. So you get some benefit from there, and that's, as we would hope. But still, the client application at the higher level is doing all the work to look for that row. The second bars represent the Skyhook approach with our CLS plugins, where the servers are actually doing the search for that row. So we get the I/O benefit, plus we get the CPU benefit, because all of those individual objects are scanning and looking for that row in parallel. So that work is pushed down into the storage system in this case. And then in the third case, so we can see we get much better scale out there in that particular case. And in the third case, this is when we add an index. So imagine we built an index on this column order key and line number, and then at query time, we can actually ask all of the servers to look for that row number, those values, if they have that row, that'll be stored in their index. So those all represent an index lookup at all the storage servers. So clearly this is a lot faster because even though in the red case the objects are all scanning themselves in parallel, in the final case they're not even doing any scanning at all. They're just consulting the local index. If they have the row, they go find it and read it out of the object and return it. If they don't return anything. So that's kind of the benefit when we put that local metadata that becomes queryable. And you could imagine also something like min or max if each object stored the min or max of this order key or line number column. That would be very beneficial at runtime to do a lookup. So another example is the range query. So now we want to not return a single row, but we want to return a range of rows. So this is about a selectivity of 10% of the data set of the billion row data. So on the left is a query that returns an integer comparison, and it returns 10% of the data set. So we sort of see the same trends here where the y-axis is execution time, and the x-axis is the number of storage servers as we scale out. And in the right-hand side, this is a slightly different query where it's looking for a regular expression. So this is going to run, the regular expression text is actually going to run on those storage servers with our plugin. Right? And that functionality is happening on the storage servers in the red bars, and that's what the scale out. And the difference here is on the right-hand side, the execution time is maybe a little bit higher because this represents maybe a little bit more CPU-intensive process rather than this left-hand side, which is integer comparison. And for integer comparison, you may consider other things you could do, like sort the data ahead of time and this kind of things. But for something a little bit more complicated, maybe like regex, that's actually running in the storage server. And you can imagine, now that we have this rich capability to write these functions and invoke them, we could do other more complicated CPU processing methods. So for instance, you might, instead of computing or looking for regex, you might actually want to compute sentiment on that text. Right? So these are the type of functions that you could push into the storage system in these cases. And then we'll wrap up. So some of the key takeaways here with Skyhook is we want to take our table data, partition it, and each partition needs to return the data semantics, and this is the feature that allows us to push that capability into the storage system, where if we can understand the data, then we can apply these rich techniques to the processing. For the RDBMS, this is a subset of a table, but for other applications, you can imagine different partitioning methods and retaining their semantics. And then we showed you how we utilize the remote resources on the storage servers with the customized object classes, as well as the local indexing mechanism that gives us the capability to do queryable metadata at runtime in the servers. I think numbers are about on time. And thank you very much. This is funded by NSF and DOE projects, as well as the Cross Center at UC Santa Cruz. And for more info, you can please visit cross or skyhookdatamanagement.com. And it's open source, so if anyone's interested to contribute, please let me know or come talk to me or contact me. I'd be happy to talk about that and happy to have you. Thanks. All right.
Can you talk a little bit about what it would take to get inserts to work? And also, could you contrast this with more traditional distributed storage layers underneath Postgres that are out there?
So for inserts, I think your first question. So this would be, inside these objects are these formatted partitions. So as the database would grow, we say we format the partition as a flat buffer. So at runtime, when you want to insert rows, the hash function will map them to a particular partition, and that tells us what object to send that row to. And then inside that object, we'll want to format that as a flat buffer as the new row comes in. So you can insert it. So the first thing that the hash tells you what object it goes to, and the second thing is inside the object, you want to make sure you store it as a flat buffer. So in fact, what's not really shown here is that inside the object is not a single flat buffer, but it's a sequence of flat buffers, because over time your data, of course, might grow as you do more inserts. So you'll have a sequence of flat buffers. And the interesting thing with that is it kind of allows us to say, with the indexing, for instance, or some other metadata if we keep around, we don't have to actually read the whole object at once and go through all the rows. We can kind of read each subsequence of the object, which is a flat buffer of various sizes. This is a tunable parameter. And that kind of that helps you constrain the amount of memory at runtime to read the sequence rather than the whole thing at once. And I think there's also some other interesting trade-offs there as well with compaction and things like that. And then I think the second, does that answer your question on that? And the second question was about the other backends. So if you think of, I guess like if you think of setting it on S3 or something like this, perhaps?
Oh, there's a number of Postgres backends.
Oh, yeah. Right. So I think the difference here, of course, there's a whole list of the FTWs on the wiki page for Postgres. This is really nice. So we work on one, developing one for Ceph. Here, for the file system, or the file-based backends, right, those are collecting scalar-gathered byte streams of files. And in this case, because we've contained the data in an object to a logical subset of the original data with semantics, that's kind of the key that lets us be able to express the functionality on that subset, just as you would in a table, but let the object do it. So retaining that semantics, I think, in this case is nice. And then Ceph just gives us this distributed, scalable capability, which then you don't have to worry about reliability or failover and things like that, because the objects are what's replicated in Ceph as well. And because it's primary copy replication, we don't have to worry about sort of, do we write to all of these at once? And Ceph sort of handles that for us as far as the inserts go. Yes.
So Redis objects are not supposed to be infinite size, right? Like you're supposed to constrain the size of each Redis object to, I don't know, 4 megs, 32 megs, 64 megs. How do you deal with too much data in those Redis objects? Because Ceph itself is not going to constrain you, but you might kill the system.
Right. So you wonder how to constrain the object size. So the parameter to tune it originally, so I think the idea is to set a large number of objects. We have several experiments, and that we have one partition per object. So we have a lot of partitions, but they're small. And then as they grow over time, they might grow too large, or maybe even individually, one might grow too large due to data skew. And then earlier I showed like a method where I think if we look back at these remote indexing real quick. Oops. If you look at the split function, and so at some point you may want to split the objects. And in this case, if you tell the object, the code, how to split, then it can actually peel out the rows you want.
In that case, you'll need to keep an index of your Redis objects, because
that would cause it. That would create different objects.
Right.
So,
you need indirection for the Redis objects, some kind of an indirection to the names of the Redis objects that you're using. Do you have that kind of indirection?
That's right. So I think you could think about, as I mentioned, sort of the object naming is what's used for lookup. So if you think of like a regularized naming scheme, you could imagine a way to split an object into two subsets, and they have a very distinct derivative names from the original object. So I think you're right, you have to keep track of that stuff, but I think a naming function helps with that. And as well, if you sort of have a lot of little partitions, the trade-off is you have some overhead because now you have more partitions, but it allows you to grow maybe a little bit longer perhaps And then coupled with the thing I mentioned where the object doesn't have to be read all at once. So maybe you have a large object, and maybe it's too large. But if you're able to peel out the sequence of flat buffers one at a time, you're not really reading one giant object here and maybe a smaller one over there. So I think that can help. Okay.
Well, the problem is not necessarily with reading the objects. It's the way Ceph and Redis works. You might not want to have.
Oh, you mean the management of the objects?
Yeah.
Yeah, that's true. Yeah, absolutely true. Yep. Ideally, we'd like to keep them uniform size and relatively small, like you mentioned. So I think that's what the split function is something we need to keep in mind for that.
Beautiful.
Okay.
Final question. Thank you.
Okay. Thanks.